We've seen now that we can construct graphs that have character labels on their edges, and these graphs could represent collections of strings, or something more complicated than a string. And sometimes we can give these graphs, the nodes of these graphs, an order that basically mimics the Burrows-Wheeler order that we're used to from building the Burrows-Wheeler matrix. And it worked for some graphs, but not for others. So for example, this graph on top, we were able to give it an order. There's the order in blue. But for the graph on bottom here, which is only different by one edge label, it's only different by that one edge label. For graphs like that, we weren't quite able to do it. We were able to fix it in that case, right? So we came up with sort of an alternative way whereby we kind of unzipped a couple of these nodes backwards from that bubble and created a slightly different shaped graph, and then we were able to, then suddenly we did have the ability to put all the nodes in a total order. Okay, but the question came up, what are these graphs? Is there a set of properties where if a graph has those properties, an edge-labeled graph like the ones here, then we know such an ordering will be there, and we'll be able to make use of that ordering when doing things like matching and such. And so now is when we can finally get to the definition of this kind of graph, which is called a Wheeler graph. Okay, we say an edge-labeled directed graph, graphs like the ones we've been drawing where we have one character labeling the edges. We say it's a Wheeler graph if the nodes can be put in an order, like the orders we were writing down before. If the nodes can be put in an order such that, okay, and we're going to write down 3 statements. The first statement, pretty much the simplest, we'll call Rule 1. And Rule 1 says that nodes that have 0 in degree, that is, they have no incoming edges, have to come before all the other nodes in the ordering. So if we write down an ordering 0, 1, 2, 3, 4, 5 on the nodes, we're going to write 0, 1, 2, we're going to write the first several, or the first however many items in that order are going to go to the nodes that have no incoming edges. Okay, so that's the first rule. The nodes with no incoming edges have to come first in the ordering. Okay? The next 2 rules both have to do with pairs of edges. Right? So that was Rule 1. Now for Rules 2 and 3, we're going to make a statement about a relationship that exists for any pair of edges in the graph. Okay, and we have 2 rules, so we're going to have Rule 2, Rule 3. Both of them are going to pertain to all pairs of edges in the graph. So for all pairs of edges, E and E prime, where we can also write the edges in terms of their source and destination. So we'll say edge E has source U, destination V, and edge E prime has source U prime, destination V prime. So for all such pairs of edges, labeled A and A prime respectively, right, because all edges have a character label, we have the following logical relationship. So this right here, we'll talk about this a little bit more in a moment, but this right here is just implies. Right? It's an idea from propositional logic. So what that says is that if the label for the edge E is less than the label for the edge E prime, right? So alphabetically less than, then, if that's true, then it has to also be the case that the destination of edge E has a lower order, is earlier in the order compared to the destination for edge E prime. Okay, so let's pause there. There were 2 different notions of order there, right? There was the order over the alphabet, for which you can see I'm using this kind of curly less than sign, right? This is a straight less than sign. This is a somewhat curly one, right? So I'm using curly less than for the alphabetically less than relationship. And then for the node ordering, right, which is a separate notion of order, there's an order over the nodes. In the node ordering, I'm going to use the normal less than sign. Okay, so if the edge label is less than the other edge's label, then the destination has to come before the other's destination in the node ordering. That's Rule 2. And this pertains to all pairs of edges E and E prime. And I'm going to review a little bit exactly what that implies operator means in a moment. Okay, so that was rule 2. Now for rule 3. Rule 3 says that if these two edges, E and E prime, have the same label, so if A equals A prime, and, that's an and, right, that symbol right there means and, if the two edges have the same label and the source of the first edge is less than the source of the second edge, it comes before in the ordering, then that implies that the destination of the first edge cannot come after the destination of the second edge, right? V less than or equal to V prime. Okay, and again, this holds for all pairs of edges, E and E prime. Okay, that's the definition. There we go. We wrote the whole thing down. Let me take another moment just to remind ourselves about what the implies operator is doing. Okay, denoted using that sort of arrow pointing to the right. Okay, so this type of statement is an implication or an implies statement, and it's an idea from propositional logic, and it's a statement that may or may not hold. That is to say, the statement as a whole may or may not be true, and to see when it holds, we have to write out the so-called truth table, right? So we've got A and B. A might be true or false, B might be true or false, and depending on whether A and B are true and false, this overall statement might be true or false. So let's write it down, all the situations. Okay, so let's say A is true and B is true, right? So if A implies B and A is true and B is true, then that makes sense, right? The implication is saying if A, then B. So in this situation where A is true and B is also true, that makes sense. So if A is true and B is true, the overall implication is true. If, however, A is true and B is false, that would mean the implication did not hold. In other words, the implication is saying if A is true, then B is true. And in this situation, A is true and B is false. So the implication does not hold. So in this case, the overall implication is false. And then the other two cases are the cases where A is false. So let's do A is false, B is true. A is false, B is false. We'll do them both. And in both cases, the implication doesn't care, right? So if the left-hand side isn't true, if A isn't true, then the implication really just has no say about what B is. So B can be true and B can be false. Either way, we say that the implied statement holds. The overall implication is true. Okay, so we write true in the last column for those last two cases. In other words, when the left-hand side is true, when A is true, the right-hand side, B, has to be true also. When the left-hand side is false, A is false, it doesn't matter what the right-hand side is. It could be true, it could be false. Either way, the implication holds. The implication is not violated. All right, so that's what we mean when we write this right arrow operator in our definition. Okay. So we've got rules 1, 2, and 3. Rule 1 is pretty straightforward. We'll see it in action more, but it doesn't really need review at this point. Rules 2 and 3 are the harder ones to wrap your head around. So let's spend a little bit more time with Rule 2. Rule 2 says for all pairs of edges E and E prime, if the label for edge E comes before, alphabetically, the label for edge E prime, then the destination of edge E has to come before the destination of E prime in the node order. So let's just make a picture with that's like a hypothetical piece of a graph. Let's say I'm looking in the graph over here and I see the edge on the right, left rather. I see this edge and it's labeled A. And then I look elsewhere in the graph and I see this edge labeled B, and they each have a source and a destination, and let's assume the sources and the destinations are disjoint. Okay. And let's say additionally that that this is a Wheeler graph. This is a piece of a Wheeler graph, and therefore this property has to hold. Okay. So if this property holds, we have first let's check to see if the left-hand side is true. All right. So over here this edge is E and this edge is E prime. So we look at their labels. We see the label for E is A and the label for E prime is B. Okay. So the left-hand side is true. Right? The left-hand side is true. Okay, so when the left-hand side is true, the right-hand side also has to be true. And what that tells us is that in the node ordering, the destinations of these nodes have to be such that the one on the left comes before the one on the right. So for example, a consistent way, a legal way to put these two things into the overall ordering would be like to say that the destination of the node up the edge on the left is 10 in the order, 10th, and the destination of the edge on the right is 20th in the order, for example. Right? So that would satisfy rule 2 in the definition. In other words, if the labels differ, the destination of the smaller label edge, the edge labeled A in this case, has to come before the destination of the larger label edge, the label B in this case. Let's see another example. So let's say again we sort of reach into the graph and we take out a little piece and we see these two edges, and in this case the two edges have a common destination. So they both point to the same node. Okay? And we don't know in this case whether the graph is a Wheeler graph. So we're trying to figure out, could the graph be a Wheeler graph? And we're thinking about rule 2, because rule 2 is the relevant one here since the edges have different labels. Okay? And what rule 2 says, again, let's say this is edge E and this is edge E prime. We have that the label for edge E is less than the label for edge E prime. So the left-hand side is true. So the left-hand side is true. Check. Check. And that implies that the right-hand side also has to be true. What does the right-hand side say? It says the destination of the edge on the left has to be less than the destination of the edge on the right, but that's not possible, right? They have the same destination. You can't have a node that's before itself in the order. It doesn't make sense. So in this case, we can see, just purely based on the shape of this part of the graph and what those two edge labels are, we can see it can't possibly be a Wheeler graph, right? The Wheeler graph property number 2 is definitely violated right here. Okay? So it's kind of a corollary of our rule 2, is that a node cannot have two incoming edges with different labels, right? That's the thing about this example that makes rule 2 break down. We've got one node, it's got two incoming edges, one's labeled A, one's labeled B. That means that the destination of one has to come before the destination of the other in the order, but this is not possible because they have the same destination. So it's a pattern like this is always going to violate rule 2. Let's now do something similar, but for rule 3. So let's bring rule 3 back. For all pairs of edges E and E prime, labeled A and A prime, if the labels are equal and the source of one comes before the source of the other, that implies the destination of the first one can't be greater than the destination of the second one. Okay, so let's take an example. In this example, importantly, the edges have the same label now, right? Because those are the pairs of edges where rule 3 is relevant, right? So let's say, again, I've taken this piece of a larger graph, and I'm just looking at this one bit of the larger graph, just these two edges from the larger graph, and they are disjoint, right? They don't have the sources and destinations of the two edges don't overlap in any way with the other. And let's say, in addition, that in the ordering, let's say we have a hypothetical ordering, and in that hypothetical ordering, we've given those nodes come 10th and 20th in the order. Okay, so the source of the one on the left comes before the source of the one on the right. Well, that implies, just like rule 3 says, that the destination of the edge on the left can't come after the destination of the one on the right. So for example, it can come before. So we could write like 30 and 40 would be, in this hypothetical example, those would be a legitimate way to order the two destination nodes here. It's just that the one on the left can't be greater than the one on the right. Okay? And in this case, rule 3 holds for this pair of edges. So we say, if the labels match but the sources differ, the destination of the lower source edge must not come after the destination of the higher source edge. It's just another way of saying what rule 3 is telling us. Let's again see a second example. Let's say we've sort of picked two edges out of the larger graph. In this case, they have a common destination, sort of like we saw in the example for rule 2. but different sources. And so one source comes before the other, and that implies that the destination of the one on the left can't come after the destination on the one on the right, the destination of the one on the right. It has to be less than or equal to. And that's what's crucial in this situation because they have the same destination. So in this case, that's actually fine, right? No problem. Because whatever number we put in here, we could put, 77, or we could put 1, whatever number we put in there, it's going to be, the destination of one edge is equal to the destination of the other edge, so that's totally fine. Let's just put like 30 in there just to complete the example. So in these two cases, looking at these pairs of edges, we do not see a violation of the Wheeler graph properties, okay, on this slide. In the previous slide, we did see a violation, but on this slide, we don't. Okay, so that was a little bit of applying rules 2 and 3 in specific situations. Let's now do something a little bit harder, which is I want to write down a graph, a complete graph, and we'll just ask ourselves, is it a Wheeler graph or not? So let's do that for some examples. Okay, so I'm just rewriting the definition in a sort of space-efficient way at the top here. And now let me start with a simple example over here. Let's do this. Say I have these two nodes, and I've got an edge coming over like this. And now let's give the edges labels. Let's say this one's A, and this one's B. Okay, and so our question is this a Wheeler graph? Okay. Well, we got to look at these properties. So let's start with property 1. Property 1 says the 0 in degree nodes come before the others. But that doesn't matter because in this case, there are no 0 in degree nodes, right? So the proposition holds trivially, right? There's actually nothing in the set of 0 in degree nodes, and so that property holds just fine. Okay, so property 1, rule 1 is taken care of. Okay. There's only one pair of edges to look at in this case, and the edges have different labels, A and B. So which rule is the relevant one? If the two edges have different labels, which rule is relevant? Rule 2 or Rule 3? Rule 2, that's the one for edges with different labels. Rule 3 is not relevant here because if I plug in these two edges for E and E prime, what I'll find is that the edge labels are equal. I'm sorry, yeah, the edge labels are not equal, and therefore this part of the left-hand side will be false, and therefore the entire left-hand side will be false, and therefore the entire implication holds trivially, right? Because when the left-hand side is false, the whole thing is false, okay? So rule 3 we know is going to hold just fine, basically, because there are no pairs of edges that have the same labels. So let's go to rule 2. We've got two edges with different labels. Rule 2 says the destination of the edge with the smaller label, the one labeled A, let's just use alphabetical order. All right, so this label comes before that label. The destination has to be earlier in the order than the destination of the one labeled B. No problem. We can write down an order very simply where we put 1 here and 2 here. Right? In other words, node on the left comes before node on the right. All 3 properties hold. That's a Wheeler graph. Okay? Check. Okay, let's do another one. Let me draw another graph here. Okay, and let's say both these edges are labeled A. A on top, A on bottom. Okay. Start with rule 1. Rule 1 says 0 in degree nodes come before the others in the ordering, and there's one such node, the one on the left. This node has 0 in degree. No incoming edges. So we have to make it come first in the order, so let's just go ahead and put a 1 there. Okay, now I've got these two destinations. In this case, the two edges in question have the same label, so rule 2 is not relevant. Rule 3 is relevant. Rule 3 is saying that if two edges have the same label and the source of one comes before the source of the other, then something. But the important part is this doesn't hold, right? In this case, the two edges have the same source. So this is false. So the whole left-hand side is false. so the implication holds. Right? The implication, when the left-hand side is false, it holds. All right, so nothing's violated here, and indeed, we actually can take our pick as to how we order these two nodes on the right. Right? We know they have to come after the node on the left in the order, but you know, we could make it 2 and 3. We could even reverse it, make it 2 and 3. Doesn't matter. Either way, we've successfully ordered the nodes in such a way that the properties hold. That's a Wheeler graph. Okay, let's try another one. All right, this is going to be kind of like the first example. This time, I'm going to give the two edges the same label. A and A. Okay, rule 1, not relevant. There's no 0 in degree nodes here. Rule 2, not relevant. There's no pairs of edges where they have different labels, so not relevant. Rule 3 is relevant, because we've got two edges. They have the same label, and the source of one is different from the source of the other, right? So for some choice of E and E prime, we're going to have the left-hand side hold, okay? But what it's saying is, the one with the smaller source has to have a destination that's no greater than the others. The one with the larger source has to have a destination that's no less than the other. But that won't work, because let's just try it, right? Let's just put in a hypothetical order here, 1 and 2. Now, if we let this edge on top be E and this edge on bottom be E prime, we have this part of the implication is true. This part of the implication is true because the source of E is less than the source of E prime. But now we're saying destination has to be less than or equal to the destination, but that's not true. The destination is greater. Destination of E is greater than the destination of E prime, so it doesn't hold. And we could do the other order and it would symmetrically still not hold. So there's only 2 orders to try. We just tried them both, and we, in neither case, could get rule 3 to be satisfied. So this is not a Wheeler graph. Okay, this is not a Wheeler graph. Let me take the 1 and the 2 away just so there's no confusion, right? There's actually no way to order the nodes so that the properties hold. So it's not a Wheeler graph. Okay? I am going to show a few more examples, but I'll skip them. It's good to go back and sort of look at each one and see why it makes sense, why each one of these is either Wheeler or not Wheeler. We looked at these 3. We just walked through those. Here's 3 more. But so far, however, we've only really been looking at these kind of small graphs. But you can already sort of get the feeling that the process of determining whether a graph is Wheeler or not, you know, it's not that simple, right? One thing that you might notice, if we think about how hard is it, like what is an algorithm that would help us to decide whether a given graph is a Wheeler graph or not, if somebody were to give us an ordering, right, say, I think this is a Wheeler graph, and furthermore, here's an ordering over the nodes, and for this ordering, I think all the properties hold. If somebody were to say that, and we just had to check whether that was true, whether for that ordering, all 3, rule 1, 2, and 3 all hold, that wouldn't be too hard, right? If you think about what we would have to do in that case, we would have to, let's look at rule 1, for example. We just have to sort of iterate over the nodes and check whether the 0 in degree ones came before all the higher in degree ones. That's really easy. So we can do that in just a loop over the nodes. Then for rules 2 and 3, it's a little more complex because in those 2 cases we have to loop over the edges. Pairs of edges, rather, sorry. Rules 2 and 3, we have to loop over all possible ordered pair of edges to test 2 and 3. Okay? But we can do that. And then for each pair of edges, we can easily check propositions 2 and 3. That's not hard. So if somebody gave us an ordering, we could check that ordering, and it wouldn't be too hard. We'd end up paying something basically like big O of the number of edges squared. Or at least that would be the important part, is number of edges squared. However, if somebody doesn't give us an ordering, then it's up to us to come up with the ordering. And there's a lot of possible orderings, right? If the number of nodes is n, there are n factorial possible ways of ordering those nodes. If we're doing it from scratch, it turns out, provably, that problem is hard. Specifically, it's NP-complete. This is shown in the literature. I have a reference here on the lower left. That's an example of a paper that shows this. Related problems are also quite hard to solve or even to approximate. So all of this is just to say this two-step process, the process of, okay, let's pick a ordering. Okay, for that ordering, I can check to see if the properties are true. If we skip the first part and just assume the ordering is given, the second part's not that hard. However, we have to do both, right? Because we have to both try different orderings and check to see if the orderings, if the properties hold under the ordering, that's what makes this quite hard. And indeed, it's NP-complete. Okay. I want to show a larger example. First of all, to sort of clarify a little bit more how hard this problem can be. But also I want to show an example that elucidates another kind of intuition for what the Wheeler graph properties are trying to enforce about the graph. And it's going to take me a few steps, but let's just start by looking at a somewhat more complicated graph here. Okay, so here's our graph. You can see it's an edge-labeled directed graph, just like we're used to. I've copied the Wheeler graph properties there in the upper right. Okay, and we're going to use alphabetical order. So I've got B, G, and R. We're going to say B comes before G comes before R. And we want to know, is this a Wheeler graph? And part of that question is, can we come up with the ordering that makes it a Wheeler graph? So let's just start with Rule 1 and see what Rule 1 says about how we have to order these nodes. Rule 1 says any nodes with in degree 0 have to come before the others. Now let's see. There is only one such node here, right? In this whole picture, only one of the nodes, this one right here, has in degree 0. So let's go ahead and give that a 0. That comes first in the ordering according to Rule 1, no question. Okay. All right. So the rest of the nodes, they do have incoming edges. They have one or more incoming edges. So let's take a look at Rule 2, because Rule 2 is going to give us some broad information about how the rest of the nodes need to be ordered. Because Rule 2 says that if two edges differ in their label, then the destination of the one with the smaller label has to be less than the destination of the one with the larger label. So the next bunch of nodes in the order are going to be the ones that are pointed to by the low alphabetical letter. So in this case, that's B. Right? So let's just sort of look at this diagram and see, where do the B edges point? Okay, we've got two B edges, and they both point here. So there's only one node pointed to by the B edges, so that must be the one that comes next, because alphabetically, B is the smallest. So, okay, so we're going to put a 1 here. We know that's got to be a 1. Okay, now then the next set of nodes in the order must be the ones that have the next larger alphabet symbol as their incoming edge label. Okay, so that would be G in this case. So let's look at all the nodes that have incoming G. All right, this node has incoming G. This node has incoming G. And this node has incoming G. So those three nodes, we don't exactly know what exact number we should put here, but we know that it's going to be 2, 3, or 4 for those three nodes. All right, in order to figure out which one it is, we'll have to move to Rule 3. Okay, but let's just stick with this coarse information that we're getting from Rule 2. And then these remaining two nodes are the ones that have R as their incoming edge label. So those 5 and 6 are going to be here and here. And now let me show you the answer, which is compatible with what we said, but with Rule 3 applied as well. Okay, so here, that was the process that we would have had to go through if we wanted to figure out that that was a Wheeler graph. Right? It was kind of, in some sense, it wasn't that hard to figure out roughly what category each node fell into, right? The 0 in degree ones first, then the ones with the next alphabet character larger, the ones with the next alphabet character larger as their incoming edge label. That wasn't so hard, but then there was more work to do to resolve the order within those, and that's should show you some of the complication of why it's not an easy thing to decide if something's a Wheeler graph. But let me show you a different picture. Let's just take this picture, and instead of using these letters B, G, and R, I'm going to use the colors blue, green, and red. You'll see why in a moment. So I'm not really changing anything about this graph, right? You can think of it as the exact same graph. It's just that I'm using color rather than just letters to represent the edges. Now let's redraw it in a particular way. The way I'd like to redraw it is that I want to take all the nodes, 0, 1, 2, 3, 4, 5, 6, same nodes, but I'm going to draw them twice in two replicas, a replica of each node along the bottom, a replica of each node along the top. The ones on the bottom are going to be what I'm going to call the out replicas. When I draw an edge, I'm going to draw it outgoing from one of the replicas on the bottom. The nodes on the top, I'm going to call the in replicas. When I draw an edge, I'm going to draw it incoming to one of the nodes at the top of the diagram. So I'm going to write all the same edges that I did before, just in this new way where I'm drawing it from the out replica to the in replica. Just as a really small example, so if this is the original graph here, how would I draw it with this in and out replica representation? Let's see, I would draw it from the out node on the bottom labeled 0 to the in node on the top labeled 1. There we go. So this representation would be how I would redraw something that I originally drew that way. Okay, so let's now redraw the graph that we were just talking about, but in this new in and out replica way. And it looks like this. And right away, now that we've drawn it this way, some interesting things kind of pop right out. Okay, so first of all, if you look along the in replicas, you can see a certain ordering, right? In fact, I can sort of partition the in replicas kind of like this, where first I've got the node with 0 in degree. Okay, so that comes first. Then I've got the node with the blue incoming edges. Okay, great. Then I've got the 3 nodes that have the green incoming edges, and then I've got the 2 nodes that have the red incoming edges. Okay, this comes from rule 2, right? Like we were saying before when we were looking at the graph, rule 2 helps us come up with this broad structure where we know that all nodes that have incoming edges with one alphabetical character, let's say it's the smallest alphabetical character, they're going to come before all the nodes that have incoming edges with higher alphabetical characters. Right, so this is just, if we look along the top, we see a representation of that phenomenon, which ultimately comes from rule 2. The blue destinations before the green ones, before the red ones in this example. Okay, we see something else too if we look at the same color edges. So if we look at the edges that are the same color in this diagram, something you might notice is that they never cross. So they don't cross each other. They never overlap. So there's no examples here. Like, for example, if I were to draw in a new edge like that, then you'd say, wait a minute, they cross right here. But there's no examples here of 2 edges of the same color crossing. And this fact holds in general, and it comes from the 3rd rule from the definition of the Wheeler graph. Because what that's saying is that if you have 2 edges with the same label, if the source of one comes before the source of the other, right down here, if the source of one comes before the source of the other, the destination can't be greater than. They can't cross. It's the same concept, right? So no 2 same color edges are allowed to cross each other. Okay? So it's just another way of visualizing the same kind of graph, but now the rules have kind of a visual interpretation. Okay? In terms of the looking across the top and seeing the different partitions, and in terms of looking across the bottom, or looking across the edges and seeing no crossing same color edges. There's also, if you look at the top and the bottom of this diagram, the in and the out replicas, there is a hint of the Burrows-Wheeler matrix, right? Because the top is a bit like the F column from the Burrows-Wheeler matrix, right? The F column had this very special structure where first we had the $sign, then we had all the, then we had chunks, blocks for each alphabet character. And that's kind of what the top row of replicas looks like here. We've got the 0 in degree node, and there's only one in this case, but there could be more than one. We've got the 0 in degree node, we've got the nodes with blue incoming edges, the nodes with green incoming edges. Sort of the same thing as the F column of the Burrows-Wheeler matrix. And then, therefore, there's something about the bottom that's kind of mimicking the L column for the Burrows-Wheeler matrix. We'll have more to say about this. We haven't really yet talked about how to do matching on the Wheeler graph. That comes next. But at least for now, looking at the diagram this way, you see something somewhat reminiscent of the F and L columns of the Burrows-Wheeler matrix. Okay. So before we conclude here, let's bring back a graph that we were looking at previously, this one down here, okay, which we were using to represent just a pair of strings with just one difference in the middle. And let's ask, is this graph a Wheeler graph? I'll just leave it here for a moment. You can maybe like pause the video and see if you think that this is a Wheeler graph. Okay, now that you've formed your opinion, no, it's not. We can see it's not, for example, if we just zoom in right here. Because what we have there is a situation where a node, the one over here, has two incoming edges, and they have different labels. That violates Rule 2, because Rule 2 says that if you have two edges with different labels, the destination of the smaller label has to be less than the destination of the larger label. In this case, they have the same destination, so it doesn't work, right? We said that was a corollary of Rule 2, is that a node can't have two incoming edges with different labels. So no, this is not a Wheeler graph. So even though it had, we were saying before that it had that property, so why does it turn out that this isn't really a Wheeler graph? It's just that we had to draw the edges the other way. So let's just switch the direction of all the edges in this diagram. Just like that. If we flip the edges to follow the direction of the matching, now it is a Wheeler graph. Okay? I say we're following the direction of the matching because just like with the FM index, we're matching longer and longer suffixes of our pattern. So in this example, we're sort of moving right to left. So I've just switched the edges to point in the right to left direction, and now we do have a Wheeler graph. Okay, so let's look a little bit harder at how it has the Wheeler graph properties. So let's look at property 1 first. Property 1 says 0 in degree nodes come before the others. There we go. Right, that node was always first in the orderings that we wrote down, and it's the 0 in degree node in this picture. So far so good, right? The definition of Wheeler graph applies here. Now we have Rule 2. Rule 2 says let's use alphabetical order, so A before C, before G, before T. So the destinations of all the edges labeled A need to come next in the ordering. Okay, so those are going to be these nodes, this one, this one, this one, right? There's only 3 of them? Yeah. So those 3 will come next. And indeed, here we go, 1, 2, and 3. Then the ones at the destinations of the edges labeled C should come next. Indeed, 4. The ones at the destinations of the nodes labeled, the edges labeled G should come next. Indeed, 5 and 6. Now for the ones at the destinations of the edges labeled T, 7, 8, 9. So yeah, Rule 2 is satisfied, right? We've got these sort of classes whereby the destinations of the nodes labeled A all come before the destinations of the edges labeled C, which all come before the destinations of the edges labeled G, etc. So 2 is satisfied. 3 is also satisfied, though the specifics of that I'm just going to leave as an exercise.